Welcome back to the deep dive. We got a really interesting paper today. It's called Seaweed-7B. And just for the quick version up front, this paper is about a new video generation model, 7 billion parameters, which sounds big, but it's actually quite efficient. They trained it on about 1,000 H100 GPUs for less than a month, and it's performing surprisingly well, like comparable or even better than giants like Sora, VO 2.0, 1.2.1 on tasks like text to video and image to video. The key seems to be, well, a lot of things. Optimized design, careful data work, clever training, stuff like VAE Compression, new attention ideas, multi-stage fine-tuning. Oh, and it's way faster at inference. All right, let's get into the details.
Yeah, it's definitely a paper worth digging into, especially, with everyone else building these enormous models. The paper makes a good point right at the start. These huge models are impressive, sure, but the cost. Training is one thing, but inference cost is a major hurdle.
Totally. You hear about models like Movie Gen needing thousands of GPUs just to train. And this paper really hits on how expensive it is just to generate one video for a user. It's way more than text or images. That kind of cost really limits where you can actually use these things, right?
Yeah.
Forget blowing it widely on social media if every video costs a fortune to make.
Exactly. And that's the problem Seaweed-7B is really trying to tackle. It reminds me a bit of what happened with language models. You had models like Mistral-7B or DeepSeek V3 come along, smaller but smarter designs, outperforming bigger ones. So the Seaweed team probably looked at that and thought, can we do something similar for video?
It's a great parallel.
Yeah.
Because, like the paper says, there hasn't been as much focus on that kind of efficiency in video. The smaller video models we've seen before, well, they often just didn't match the quality of the big ones.
Right, exactly. Seaweed-7B is positioned as their answer to that gap, aiming for something you could potentially run on a single GPU, really optimized for FLOPs. And the training resources, they quote, under a month, about 1,000 H100s, 665,000 H100 GPU hours total. It shows that efficiency was a goal right from the beginning.
So the mission is clear. Great video quality, but without breaking the bank. The paper breaks down their approach into data, model architecture, and training. Let's start with data. Sounds like they were pretty meticulous there.
Oh, absolutely. They detail this really thorough data pipeline. It starts with spatial cropping. They used FFmpeg's crop detect to get rid of black borders, which is pretty standard, but then they went further. They built frame-level models to spot things like text overlays, logos, watermarks, even special effects baked into the frames.
That makes sense. You don't want the model learning to generate watermarks.
Yeah.
So how did they decide what to crop based on those frame detections?
They developed this bounding box aggregation algorithm. The idea is these overlays are usually pretty consistent frame to frame. So the algorithm looks at the detections across frames, checks confidence, sees how much the detective boxes overlap using IOU, intersection over union. Then it aggregates these into larger bounding boxes, covering the unwanted stuff for the whole clip. And a heuristic decides the best crop region to avoid those boxes. If it can't find a good crop, the clip just gets tossed.
Okay, that sounds pretty robust for cleaning up the visual frame.
Yeah.
What about the quality of the videos themselves? Like, were they blurry or shaky?
Yeah, they tackled that with multi-stage filtering. First, basic stuff. Duration limits, minimum resolution, short side at least 256 pixels, and aspect ratio checks. Then, more advanced visual quality checks. They trained another model just to score aesthetics and clarity. And importantly, they didn't use one single threshold. They set thresholds manually based on where the data came from and what kind of video it was, a bit more nuanced.
Right, recognizing that, say, user-generated content might look different from a professional shot. What else did they filter for?
Motion. They wanted to get rid of static clips or ones with weird motion. They used an improved motion amplitude aggregation algorithm. They mentioned it was based on motion vectors, and it was way more efficient than using optical flow for their needs while giving similar results. They also filtered out excessive camera shake, weird playback speeds using a high FPS detector, plus safety screening for harmful stuff and artifact detection, things like slide transitions, jitter, oversaturation.
Wow, that's a comprehensive checklist. Did it make a big difference?
The paper mentioned something about the unusable clip rate.
A huge difference, yeah. They said it dropped the rate of invalid clips from something like 42% down to just 2.9%. They double-checked with manual evals, too. It really highlights how critical good data is.
No kidding. Can't build a good model on bad data. Now, beyond just individual clip quality, they also talk about data balancing and deduplication. Video data tends to have tons of common stuff and very little of the rare stuff, right? Precisely, that long-tail distribution problem. To handle that, they used clustering. They looked at both visual features using a CLIP-like model and semantic features from captions generated by an LLM. This gave them over 10,000 clusters. It helped them find and remove duplicates, which is crucial with massive data sets. But more importantly, it let them downsample the really common categories, the head of the distribution, to make things more balanced without losing too much diversity. And they say this was pretty cost-effective.
That's smart. Balance it out without just throwing away data. And I saw they also mixed in synthetic data from simulations.
Yes, they did. They generated synthetic videos using 3D scene simulation, like graphics engines. The goal was specifically to improve things like 3D consistency during camera moves and keeping human bodies looking right during complex movements. They generated millions of these synthetic clips and mixed them in with the real-world data during training.
Interesting. So using synthetic data to target specific weaknesses.
Right.
What about the captions? They mentioned training a captioning model and this idea of system prompts.
Right. Good captions are obviously key for prompt following, so they trained their own captioner. And they generated two kinds of captions for all their training data. Short ones, just focus on the main action, and longer, more detailed ones describing the scene, objects, visual style, everything. They used a pre-trained CLIP vision encoder and an LLM for this. Figure 1 in the paper has some examples. It's pretty neat.
Two types of captions. Interesting. And the system prompts, what are those about?
System prompts are like extra metadata tags they added. Things like video type professional versus user gen camera position, angle, movement, visual style. Some came from metadata, others from high confidence classifiers they trained. During training, they'd randomly pick some of these system prompts and just append them to the regular caption. The cool part is you can then use these prompts during inference too for more control over the output style.
Ah, I see. So it's a way to inject more control signals without needing tons of explicit labels for everything. Okay, data curation sounds incredibly thorough. Let's switch gears to the model itself. The VAE and the DIT, the Diffusion Transformer.
Okay, starting with the VAE, the Variational Autoencoder. Figure 3 shows it. It's a causal 3D convolutional setup for both the encoder and decoder. Causal in time is the key bit here. It means it processes frames sequentially, only looking at past frames. This lets it handle images and videos the same way an image is just the first frame. It also means you can stitch together generated clips smoothly and handle variable length videos easily. No weird stitching artifacts.
Makes sense. Very flexible. They mentioned two VAE versions, 48 hat and 64 hat. What's the difference there?
It's about the compression ratio, how much it shrinks the video data. Equation 1 defines it. The 48E VAE had certain downsampling factors, DT4, DH8, DW8, C16, while the 64 VAE compressed more spatially, DT4, DH16, DW16, and C48. Higher compression, like in the 640E, means a smaller latent space, which should make the DIT part faster or more efficient. But you risk losing too much detail for good reconstruction.
Right, the classic trade-off. And they made an interesting point, comparing compressing inside the VAE versus using patchification later in the DIT. Can you break that down?
Yeah, that was quite insightful. So, patchification in a DIT basically groups tokens together to shorten the sequence length, reducing the attention cost. They compared two ways to get roughly the same final sequence length and attention cost. Option 1, use the high compression 6.4 VAE and no patchification in the DIT. Option 2, use the lower compression 4.8E VAE, then patchify the latent codes before the DIT. And they found that option 1, compressing more earlier in the VAE, actually worked better. Figure 6 shows the 6.4 VAE converged faster and reached a better loss. And surprisingly, even with that higher spatial compression, they didn't see noticeable artifacts in 720p generations. It suggests maybe doing that heavy lifting early in the VAE is more effective than trying to patch things up later in the DIT. Perhaps preserving temporal detail early matters more.
That's a really cool finding. Okay, so that's the VAE. What about the DIT, the latent diffusion transformer that does the actual generation in the latent space?
They started with a dual-stream DIT. Separate paths for processing video tokens and text tokens, each with its own self-arrangement and feed-forward networks. But they tweaked it into what they call a hybrid stream. They use SWI-GLU activation, not GLU. And for efficiency, 8 a single for time step modulation. Plus, they shared about 2/3 of the feed-forward network parameters in the deeper layers. This hybrid setup apparently converged faster than the standard dual stream, even with the same parameter count and compute budget. Figure 8 shows that.
Sharing parameters deeper down, nice trick for efficiency. What about attention? That's always a big compute hog.
They looked at 3 main types. Full attention, every token attends to every other token. Spaceful attention, alternating full and spatial only attention. And sparse window attention, attention only within local windows. Figure 9 has visuals. Their scaling analysis in Figure 10 showed something interesting. Full attention scaled, better lost, dropped faster with more compute. But for text-to-video quality, the benefit wasn't always huge. However, full attention did seem better for image-to-video, giving more consistent motion. They also tried a simple 3D window attention, like 1x2x2 windows alternating with 4x1x1. With limited compute, this sparse method actually got lower loss initially, but give it more training steps and full attention eventually won out, figure 11.
So full attention is best if you can afford it, but window attention is a decent fallback if compute is tight. What did they end up using?
They did something practical. They pre-trained with full attention to get that good scaling. Then they fine-tuned using window attention. The idea was to cut down on redundant attention calculations during inference to make it faster, hopefully without hurting quality too much if the fine-tuning is done right.
Best of both worlds, sort of. Okay, let's talk training strategy and optimizations. How did they manage the cost?
They used a multi-stage approach. Started pre-training just on low-res images, building that basic text-visual connection, then joint image and video training, mixing them in batches. An interesting finding was that even just including a few high-res images during that initial low-res image pre-training helped the model generate high-res video later, zero shot. Pretty neat generalization.
Wow, that's a nice bonus. They also mentioned post-training, supervised fine-tuning, SFT, and RLHF. What was the goal there?
Yeah, post-training was separate for text-to-video and image-to-video. The aim was really polishing the output better aesthetics, motion, structure. For SFT, they got about 700K high-quality videos, human annotated for balance, and even weighted the absolute best 50K videos more heavily. Figure 13 shows SFT definitely boosted aesthetics and color. But there's a catch. Figure 14 shows it could also overfit, hurting prompt following and motion quality sometimes.
Right, the classic fine-tuning dilemma. Improve one thing, maybe break another. How did they fix the potential downsides of SFT?
That's where RLHF, specifically Direct Preference Optimization or DPO, came in. They used it to fix the motion and structure issues that sometimes cropped up after SFT. They adapted DPO for video, even mixing in the SFT loss for the preferred samples. Used a really small learning rate, large beta value. They gathered preference data showing humans pairs of generated videos and asking which is better. Figure 15 shows DPO worked well, improving structure and motion. Oh, and they found changing the reference model during DPO rounds didn't help, unlike some LLM results, so they just stuck with the SFT model as the reference.
Interesting. And I saw a specific tweak for image-to-video DPO.
Yes, good point. For image to video, you really want that first frame to stay true to the input image. Standard DPO might mess with it, maybe oversaturate it, so they separated the loss. For the first frames latent, they used the standard diffusion loss. For all the other frames, they applied the DPO preference loss. Very targeted fix.
Clever. Okay, beyond SFT and DPO, they list a ton of other training and inference optimizations. These must have been crucial for hitting their efficiency goals.
Oh, definitely. They used 3D parallelism data, context, model sharding with FSDP, and Ulysses, essential for handling long video sequences efficiently in distributed training. They also tackled load balancing. Training with mixed images and videos is tricky because they take different amounts of time to process, so they built runtime balance. It uses an offline lookup table, sequence length maps to actual runtime. During training, it estimates runtimes for samples in a batch and distributes them smarter across GPUs. Does it asynchronously for the next batch, too, to hide the overhead.
That sounds way better than just guessing based on sequence lengths. What about memory? Always a killer with big models and long inputs.
Yeah, they introduced MLAC multi-levels activation checkpointing. Figure 16 explains it visually. Basic activation checkpointing saves memory, but trades it for recomputation. MLAC is more fine-grained. It lets you save activations to different places, GPU memory, CPU RAM, even disk. It prioritizes saving outputs of expensive ops. And it can even offload activation inputs to CPU disk, potentially getting zero GPU memory use for activations in some modules. Allows bigger models, longer sequences, plus asynchronous caching and prefetching.
Whoa, that's some serious memory management engineering. Any other low-level stuff?
Fused kernels. Lots of ops, like normalization, ROPI calculations, are memory-bound, not compute-bound. So they fuse consecutive I/O-bound ops into single CUDA kernels, keeps intermediate data in fast on-chip memory, registers, shared memory, reduces trends to slower global memory, improves arithmetic intensity, speeds things up. Applied this to QK norm, ROPI, attention preprocessing. They also did VAE-specific stuff, like causal chunking for memory saving during encode code, enabling high res on one GPU sometimes, and multi-GPU pipelines for even higher res.
They really squeezed efficiency out of every corner. One last thing they mentioned was a Rephraser. What does that do?
Yeah, the Rephraser. They noticed that using prompts written like the captions from their high-quality training data often gave better-looking, smoother videos. So they trained an LLM, a 7B one, to rewrite user prompts to sound more like those good training captions. Created a data set of user prompts paired with detailed captions, fine-tuned the LLM, generated multiple rewrites per prompt, then used DPO again to pick the best ones, balancing aesthetics and staying true to the original meaning. It can apparently improve the look of the output quite a bit, but they do warn it might slightly compromise strict prompt following, especially for really complex prompts. Another trade-off.
Makes sense. Sometimes you want artistry, sometimes precision. Okay, so after all that work, how good is Seaweed-7B? Let's look at the results.
Okay, evaluations. Quantitatively, for image to video, they used ELO ratings for Magic Arena humans, comparing outputs side by side. Table 3 shows Seaweed-7B ranked second overall. That's huge. It beat models like Sora and VAE 2.0, which are much larger. Really validates their efficiency focus. They also did fine-grained comparisons, figure 18. Seaweed-7B beat Sora 1.2.1, hung you on video on most aspects: visual quality, motion, prompt following, image consistency. It was slightly behind Kling 1.6 HD on visual quality, but they think that's just because they tested Seaweed at 480p, 720p mostly, while Kling was 1080p. Probably an output resolution thing.
Okay, so likely not a fundamental quality gap there. What about pure text to video?
Also very strong. Ranked in the top 2 in ELO, just behind VO2, but ahead of 1.2.1 14B and Kling 1.6 HD. Figure 19 has more detailed comparisons against VAE 2.0 and 1.2.1. Again, shows it's right up there with the big players, despite the size and resource difference.
Really impressive performance. And inference time, you mentioned it was faster. How much faster?
Table 4 compares it to 1.2.1 directly on an H100 GPU. 1.2.1 needs 50 steps, which is 100 neural function evaluations, or NFEs. Seaweed-7B, through distillation, gets good results with only 12 NFEs. The result: Seaweed-7B is about 62 times faster end-to-end than 1.2.1, while having better or similar quality. That's a game changer for speed.
62 times. Wow. And finally, how did their custom VAE perform just on its own for reconstruction?
They benchmarked it on UCF 101 and MCL JCV datasets. Table 5, metrics like RFED, LPFPS, PSNR, SEM. Their VAE got state-of-the-art results across the board. Especially notable was the LPIPS score on the tough MCL JCV dataset, high-res long videos. It was the best, even with higher compression than rivals. Figure 20 shows qualitative comparisons too, looking very competitive on detail and fidelity.
So the core components are solid too. The paper wraps up mentioning potential applications.
Yeah, they list quite a few. Obviously, image to video, video transitions. They mention a project called Omni-Human 1 for realistic human animation. Also, ideas for longer videos using long context tuning, even mixing video and text for storytelling. The speed opens up real-time generation with something called Seaweed APT, one-step generation, super resolution, camera control using their synthetic data. Lots of possibilities.
It really sounds like a versatile and potentially very impactful model.
Absolutely. The paper really drives home their main point. You don't necessarily need planet-sized models. Smart design across the board data, architecture training can get you top-tier performance with way fewer resources. They hope it spurs more research into these efficient medium-sized models for video.
Yeah, it's a great takeaway for everyone listening, especially if you're in the AML space. It's proof that clever engineering still counts for a lot. It's not just about throwing more GPUs at the problem. It definitely makes you think, right, does this open the door for smaller teams or new kinds of real-time video apps? What research paths look more feasible now that we see what optimized media models can do? Definitely something to ponder. If you want to dig deeper, absolutely check out the Seaweed-7B project page, seaweed.video. They'll have more examples and info. And the paper itself cites a lot of related work worth exploring. Thanks for joining us for this deep dive.